Hello everyone, welcome to the 21st lecture of NPTEL course on scalable data science. I am Professor Saurangshu Bhattacharya from Computer Science and Engineering Department at IIT Kharagpur, and today we are going to discuss about stochastic optimization. So, in the first part of this lecture, we have discussed the stochastic optimization problem, and we have discussed the stochastic gradient descent algorithm, and we have described proof for the stochastic gradient descent algorithm as to why and in what sense does the stochastic gradient descent algorithm converge. Okay. So, in this class we are going to discuss about the practical aspects, like we are going to discuss the mini batch SGD and the distributed SGD, and we are going to discuss some other practical considerations while implementing SGD, and then very importantly we are going to discuss some very recent advancements on stochastic gradient descent, many of which have actually led to significant improvement in running time, and they have also arguably led to the revolution in the deep learning community. Okay. So, this we have already discussed. So, machine learning is a stochastic optimization problem, and you can solve it with the stochastic gradient descent algorithm, which is this algorithm, and we know that the algorithm converges or the loss function of the parameter, or the loss of the parameter converges in the expected sense as you increase the number of updates or epochs. And this is the typical picture of convergence. So, even though normally you would look at it and say that this is really a very oscillating sequence, but actually in expectation it is converging something like this, it is going something like this. So, this is indeed how stochastic gradient descent works. Okay. So, now what are the issues with stochastic gradient descent? So, the first issue is that the convergence of stochastic gradient descent is very sensitive to the learning rate, or this eta that you use. Okay. So, you remember that in the proof we have given two conditions for eta. So, the first condition is that summation over summation over t is equal to 1 to infinity, eta t squared should be finite. So, should be less than infinity, okay, and summation over t is equal to 1 to infinity, eta t should be tending to infinity. Okay. So, this is the condition that we have put. So, there may be there may be many types of sequences which satisfy this condition. So, for example, so 1 by t to the power, let us say, so 1 by square root of t is one such sequence, which is that if you take eta, so your sequence of eta t is something like this. Okay. So, this sequence satisfies these two conditions. You can check that this sequence satisfies these two conditions. Okay. So, so the question is, what type of convergence rate do you choose? So, okay. So, we will come to that. Okay. Before we come to this, so we would like to describe what is called the mini batch stochastic gradient descent. So, we have seen the batch gradient descent, where if you have let us say n examples, you choose all the examples in computing the gradient. Okay. If you use the stochastic gradient descent algorithm that I have just described, you use one example per iteration or one example per update. Okay. So, you need not, so these are two extremes. Instead, you can select maybe a certain constant number. So, you can select m examples, m randomly selected examples to compute the gradient at each step or at each update, and then perform SGD. Okay. So, this version of SGD is called the mini batch SGD. So, this is the first and you can show that by similar arguments that this version of the SGD also converges. Okay. So, this is the first improvement, and it is seen that the oscillations, so if you look at the curve of SGD, you see oscillations of this type. So, these oscillations become much less. So, with as the number of examples that you use in each mini batch increases, the amount of oscillation reduces a lot. Okay. So, so this is one simple but very useful trick that people use to to make SGD converge better. Okay. The another important outcome of this heuristic of using m examples, okay, for each update is that it allows for parallelization. So, you may choose these m examples from m different servers and then do an update, or you may do update based on m different examples from a given server. Okay. So, all of these schemes are possible. So, there are various ways like all reduce SGD, then there is the parameter server, which is like the centralized update which we normally discuss, and then there is also some kind of round robin SGD where in a round robin fashion the parameters get updated in each of the servers. Okay. So, all these types of parallelization or distributed processing is possible. Okay. So, here is one concrete example. This is also historically one of the very important steps. So, this is by Leon Bourtu. It is due to a paper in 2008 by Leon Bourtu, and what he did was, so he was so this sort of led to a resurgence or renewed interest in this algorithm of stochastic gradient descent. Okay. So, what he did is he took a large text classification corpus. So, you have 781,000 training examples and 23,000 test examples, and you have about 50,000 features, which is the number of words in the vocabulary that were considered. Okay. And then he is trying to, so the problem that he is trying to solve is to predict the category of a document. So, there are a certain number of categories and he is trying to predict the category of a document. Okay. And So these are the questions basically that you want to ask when you have implemented this SGD algorithm. So, is it successful at minimizing the objective function? Okay. How quickly does SGD find the minimum objective function, and then what is the error on a test set? So, note that even though generally it is true that, so the objective function in case of this kind of training is typically the loss on training set. So, loss on training set. Okay. This may or may not reduce the loss on test set. Okay. So that is another thing that depending on how well the model generalizes. So these are the running times. Okay. So you see that so at that time whatever was the standard SVM solver, that took 23,000 seconds, and there was a fast SVM solver which took 66 seconds to solve, and all of them have, and the SGD SVM that Leon Bottou implemented took only 1.4 seconds. So, this was a huge speed up. Okay. And this speed up, so this speed up comes, so this is the value of the objective function and this is the test error. So, see that it comes at almost no compromise with either the value of the objective function or the test error. Okay. So, the answer was that all three metrics are better for SGD in solving SVM than the existing algorithm. Now, this graph is on the x axis, it is showing how well the different algorithms, either SGD or a conventional SVM algorithm, is able to solve the optimization problem. So, x axis is plotting the optimization quality. Okay. So, this is the absolute difference between the objective function value that you achieve and the actual objective function value. Okay. And on y axis is the amount of time taken to achieve this. Okay. So, what you see here is that if you want to get within, let us say 10 to the power minus 4 of the actual objective function value, then it takes almost no time. Okay. If you want to get within 10 to the power minus 6, maybe it takes around let us say 10 seconds, whereas the existing algorithm takes 30 seconds. But if you want very high precision, so if you want to go to 10 to the power minus 7 or 10 to the power minus 8, then the time taken increases kind of exponentially. Okay. So, this increases exponentially. So, it almost never reaches 10 to the power minus 8. So, the point here is that if you want a reasonable quality solution, then SGD is good. Otherwise, you may want to go for other higher order methods, which we will come to. Okay. And this is a comparison between the SGD and batch conjugate gradient descent. So, basically the blue line here is full SGD. Okay. So, the blue line here is full SGD, and these are the SGDs for different mini batch sizes. So, this is for mini batch size of 10,000, this is mini batch size of 30,000 and so on and so forth. So, this is the mini batch size of 781,000, which is something like gradient descent. So, this curve is for batch gradient descent, okay. And this curve is for conjugate gradient descent, which is the second order method. So, the conjugate gradient descent is known to take very few steps, okay. And now, the x axis here is the time in second, and y axis is the loss on the test set, okay. So, so as you can see that they achieve a reasonable loss, not a very low loss. So, this conjugate gradient descent achieves a very low loss, but stochastic gradient descent and different mini batch versions of stochastic gradient descent achieve a reasonable loss within a small amount of time. Okay. So, like we were discussing, so we need to choose the learning rate eta. So, there are roughly so there are two types of choices. So, one is choice, so the learning rate is of this type, okay. Okay. So, one option is the learning rate of this type, okay, where the learning rate is of this form eta t by t plus t 0. So, it is essentially of the form 1 by t, okay. So, and then the question remains that how to choose eta t and t 0, okay. So, the suggestion is that you choose t 0 such that the expected initial updates are comparable with expected size of weights, okay. So, so basically the magnitude of this number and the magnitude of this update are roughly same, okay. And you choose eta, actually this should just be eta, this should not be eta t, and you choose eta such that the oscillations do not diverge, or you take a small subsample and you try out various learning rates logarithmically, something like 10, 1, 0.1, 0.01 and so on and so forth, and for whichever it does not diverge and it reduces the cost, you use that and then run on the full data set. Now, the question comes that so this is the update that one has to do. Now, the update has two components. One is the existing parameter w and other is the gradient. Now, for a large number of examples, what you can see is that this gradient is a sparse vector, something like this. So, the vector has almost all the entries as 0 and only a few entries which are non-zero. So, you can store the vector something like this, that the 4th entry is 1 and the 9th entry is 5, okay. And you can also transmit the vector like this. If this is the case, you can break the update into these two steps. So, the first step is that you update using only the loss part, not the regularizer. So, this term comes because of the regularizer, okay. So, you update it only with the loss part and then you do further update of w as w times 1 minus eta. So, this will basically do this kind of an update. So, this is one practical way of speeding up the procedure. So, this is the basically the update. So, you store V and you store S, and then you perform the step 1, which is the first update every time, because this one depends on the examples and this changes, but the second update is just an updation of the scalar. So, you perform this maybe with much lower frequency. So, next question comes that when you are training machine learning models with stochastic gradient descent, how do you stop? So, one way of stopping is that you can do early stopping with a cross validation. So, you create a small validation set, and instead of computing the loss on the entire training set, which is a very large set, assuming, because that is why you are using SGD in the first place. So, you create a small validation set, you compute the cost function on the validation set and stop when the loss stop decreasing. Okay. And then another way of doing the same thing is that you extract two disjoint subsamples A and B of training data. You train on A and stop by validating on B. So, the number of epochs you need to complete the training on A gives you an estimate of number of epochs. Then you train on the full data set using that many epochs. So, let that be K. So, you train on the full data set using that many epochs. Okay. So, these are the practical considerations for implementing SGD in an efficient manner. Okay. Now, this is just this is the same SGD algorithm that I have described. Now, one of the main problems of SGD is that, let us say, if you have so here in this figure, what we are describing are equipotential contours. Okay. So, equipotential contours. Okay. So, basically all these lines here have the same value of the objective function. So, this is one way of visualizing a function. Okay. Now, you see that the function is more or less flat in this direction, and the function is very steeply increasing or decreasing in this direction. Now, whenever you have a function with this kind of a property, what SGD does, it oscillates a lot. This is also a property of gradient descent, not just stochastic gradient descent. Okay. So, it oscillates a lot. So, one way of stopping this is to use what is called a momentum term. So, let us say your objective function is j of theta. Okay. So, with normal SGD, if for reference, if we go back, with normal SGD you have to so you just update, your parameter is now theta, and you update theta using eta times gradient of j of theta at xi and xj. Now, here your update is of this form, that you use eta times j of theta at the gradient of j of theta, but you also store the previous gradient or rather the previous update value and you multiply that with gamma. Okay. So, the whole update at time t is what is called V of t, which is the sort of a momentum update. Okay. So, momentum update because you have a certain update coming from j of theta and you have a certain existing update coming from the previous updates. So, on the axis on which the updates are consistent. So, for example, on this axis the updates are consistent, it is always going towards the right. Okay. So, then on that axis the momentum will cause the update value to increase, whereas on the axis like this axis where you are continuously overshooting the minimum, okay, the update value will be low. So, this causes a lot of speed up of the stochastic gradient descent. So, this is one of the very important techniques of speeding up stochastic gradient descent. So, your update changes in this manner. So, every time instead of doing the previous update, you do the momentum update. Now, another, so based on this momentum updates, another very important type of update which was discovered by Nesterov, and this also has theoretical importance, but this update is that you do sort of a prescient momentum update, that is you know beforehand that you are going to do a momentum update. So, what you do is that you calculate the gradient at a point where you would normally be after the momentum update. So, instead of calculating the gradient where you are currently, okay, you calculate, you already know the momentum term. So, you calculate the gradient at a place where you would be if you were to do update only based on the momentum, and then you use that as the corrected version of the gradient. So, instead of using the gradient, you use the corrected version of the gradient for updating. Okay. So, this is called the Nesterov accelerated gradient descent. So, so this was originally proposed by Nesterov and also proved by Nesterov to converge on convex functions, but now people have also been using this in the deep learning setting, for example, for non-convex functions. Now, another important update is to use the second moment of the gradient vector to estimate the magnitude of the update in a given direction. So, also sometimes called root mean square update, because what you do is you estimate the, so for each coordinate of the gradient, you estimate the you try to estimate the square of the gradient in a momentum fashion. So, you estimate the square of the gradient, square of the current gradient, and you estimate the square of the existing gradient, and you use some fixed weighting of the two. You can use also any other weighting. Okay. So, the main idea here is that whatever gradient you have. So, if you have let us say the ith coordinate of the gradient, you divide it by square root of this expectation of g I square, okay, or it is the same thing. So, you do it using expectation of square root of g I square, and then in order to avoid division by 0 errors, you add epsilon. So, this in some sense gives you a normalized update direction rather than so your update is not very perturbed because of the magnitude of the gradient itself, and then you do this update step. So, this is called, this algorithm is called the RMS prop algorithm. This was first described by Geoffrey Hinton in one of the courses. So, many related algorithms have come up like ADA delta and ADA grad, and then the final algorithm which combines both the momentum and the root mean square updates is what is called the Adam algorithm. So, basically in order to in addition to storing an exponentially decaying average of past squared gradients like RMS prop, Adam also keeps an exponentially decaying average of past gradients. Okay. So, M basically stores the exponentially decaying average of past gradients as we have already discussed, and V stores the exponentially decaying average of past gradients, and then you debias them using by dividing them by 1 minus beta to the power t, and then this is the same RMS prop update step that you apply, and this is one of the most widely used optimizers today in deep learning community. And this graph shows a comparison of many of these update algorithms. So, so x axis is the number of epochs and y axis is the accuracy on the validation set. Okay. So, so as the algorithm progresses, the accuracy on the validation set increases. So, as you can see, these are so the blue line is for constant constant step size. So, this is simple SGD with constant step size. Red is SGD with exponentially decaying step size, and there is step decay and ADA grad and ADA delta. So, the thing to note is that RMS prop and Adam reach the sort of the highest level, and though here it is not clear, but usually Adam reaches the reduces the cost a bit faster than RMS prop, but both RMS prop and Adam optimizer work very well in practice. Okay. So, these are the references. So, the proof of SGD that I showed was from a paper by Yuri Nesterov. The stochastic gradient descent algorithm itself and the experiments by Leon Bertou were taken from the MMDS slides, and the material on the latest advancements on stochastic gradient descent algorithm was taken from an excellent blog by Sebastian Ruder, and I would recommend that you read this for the other algorithms. So, there are some algorithms which I have not described, like the ADA-grad algorithm and the ADA-delta algorithm, and these are some cutting edge things which have happened. So, for example, ADAM was invented in 2015, and then the last reference is for the graphs or the comparison, empirical comparison between the different optimizers. Thank you.